Okay, so we just saw a graphical interpretation that the solution to the Hicksian demand is given by the same tangency between the budget line and the indifference curve as the Walrasian demand, which means that it's the same quality between the marginal rate of substitution, which was the slope of the indifference curve, and the ratio of prices, which is the slope of this budget line. And so we saw a graphical reason why the same tangency holds, but we can look at it from the Lagrangian also. So let's take the old example from a previous lecture where the utility was log x plus log y. Prices were given by 1, 2. 1 is the price of x, 2 is the price of y. And remember that when you had income I, the indirect utility, so the utility of the optimal solution was ln I squared over 8. So what is the cheapest bundle that maybe gives me the same utility as I squared over 8, log of I squared over 8? So what is the expenditure minimization problem? Well, our inputs, our parameters are a price vector 1, 2, and a utility level log of I squared over 8. And we want to minimize the expenditure subject to getting the utility higher than that level, right? So we can write the Lagrangian out. We're minimizing something, so that's like maximizing its negative, right? So we're minimizing the expenditure. The expenditure is x plus 2y. X is the amount of x, y is the amount of y. 1 times x is the price, the expenditure on x. 2 times y is the expenditure on y. Minus our Lagrange multiplier times our constraint, and our constraint is that the utility level must be bigger than the total utility. The utility level must be smaller than the total utility generated by the bundle. Take our three first order conditions, x, y, and lambda. You get these things. I'll let you ponder the arithmetic on your own. You divide Lx by Ly. You get that x over y is equal to 1/2. Y over x is equal to 1/2. So y equals 1/2 x. You plug that into the constraint. So remember, in the past, we plugged everything into the budget constraint. Now we're plugging into this utility constraint. It's the same idea. And you end up with ln x plus ln 1/2 x equals ln I squared over 8, which is to say that x squared over 2 equals I squared over 8, which is to say that x is equal to I over 2, and y is equal to, this should be, yeah, that's right, I over 2, and y is equal to I over 4. So what you should notice is this is exactly the same utility that would have been received. This is exactly the same as the Walrasian demand under income I, right? So what we said was, okay, you're gonna, that should look a little magical, but once we start to break it down, it's always the case. So what did we do? We took an income I and we said, what is the value, what is the utility value of that income in the Walrasian world? That was ln squared over 8. Then we set that as our utility target, and we said, what's the cheapest way to generate that utility? And it turns out the cheapest way to do it is the Walrasian demand. In other words, given the utility that's generated in the Walrasian problem, you're acting as an expenditure minimizer. And likewise, given the expenditure of the Hicksian problem, that's the most utility, given the expenditure function of the given the expenditure in the Hicksian problem, you're maximizing your utility subject to that particular level of expenditure. So we can summarize this relationship between the dual problem and the original problem, the Walrasian and the Hicksian problems, through this enormously intimidating looking set of equations. So the first time I saw this, I was like, this is crazy. I just memorized them mnemonically. HPV equals X star, XPE equals H star, blah, blah, blah. In my head, I didn't learn it. I just memorized it. Don't do that. Don't do that. Please don't do that. We're going to go over this a lot. We're not going to memorize these equations. I don't care if you ever learn the equations themselves. What you need to know is what they represent, and therefore, if you look at one, how to understand what it's saying, right? So if you see these equations, you should be able to understand them. You don't need to be able to create them yourself. So please don't spend needless effort memorizing them. But it's very important that you do learn what they mean. They're the reasons we study the Hicksian problem. So what they're saying is that H star of PV is equal to X star. Let's break out the first one, and let's riff a little bit on it. So So the first thing is that, so it's, let's see, it's H star, it's H star of PV of PI is equal to X star of PI. Now notice the prices are constant here all the time. So there's never a change in the prices. We set the prices once and they're fixed all the time. But notice that H star takes a price and a utility level and it returns a demand. X star takes a price and an income and it returns a demand. And the last thing is V takes a price and an income and it returns a utility level. So what this is saying is that if we first solve V and then we plug it back into H, right, because H takes a utility level, so we're going to take this V, let me change colors, we take this V and we're going to plug it in for that U there, right? That's what we're doing. We're sticking it in as the second argument of our H function, and what we're getting out is a demand. So on the left-hand side of this, we have H, which takes a price and a utility, and on the right, we have a price and an income, and we're saying that those two things are equal. They're both the same demands. And the interpretation here is, so what is X star? X star is the most utility I can get for I, right? So X star is the bundle. So X star is the most utility for income I. And H star is the cheapest for utility. And normally it would be the cheapest income for utility U, right, for some arbitrary utility. But here we're saying it's the cheapest for utility V is equal to U of X star, right, the utility associated with X star. So what we're saying is that the cheapest way to generate utility U of X star is X star itself. Okay, so I'm going to write that down. That's why I think that is the most important thing. The cheapest way to generate utility U of X star is X star, right? Because the cheapest way to generate the utility U of X star is, right, this is H star of PV of P equals U of X star, right? And this is saying that this is in fact X star. Now, what is the idea behind this, right? What is the idea behind this? Imagine there was a cheaper way to generate the utility U of X star. So say that, so instead, imagine there was some Y such that P dot Y was greater than or equal to U of X star. And, sorry, that's not what I want. I want such that U of Y is greater than U of X star, and P dot Y was less than P dot X star. Well, remember, if we work with monotone utility functions, then this is equal to I. And we said that if you're spending less than I, then you could spend the extra utility on, you could spend the extra on something else. So this violates Walras' law, right? Walras' law said that at the optimum you spend your entire utility. And this is saying that Y is better than X star and cheaper than X star. That means X star couldn't have been optimal, right? If X star was optimal, there's nothing better than it and cheaper than it, right? And that's exactly what this thing is saying. Now, if we look at the rest of the, these equations, they say the same thing again and again in different language. So X star of PE is the utility, is the bundle of the best way, the highest utility you can get with expenditure E. And that's saying that that is the same as H star. So you give me some utility level and you say, what is the highest utility you can get with the expenditure, with the cheapest expenditure to get that utility function? It's the same as the original demand. And then the following two are just plugging these things back into the E and V. So it just says, how much do you have to spend? So this is equation 3. The left-hand side says, how much do you have to spend to get utility V when V was generated as the highest utility you can get with income I? And the answer is I. In other words, what is the cheapest way to get a utility equal to the maximum utility you can get with I? It's I. If it was any cheaper, you could do better when you had income I, because you could spend that additional bit to get more utility. So if this is confusing to you, which I kind of hope it is, because if it isn't, then you're on your path to becoming a genius economist. I mean, this is hard stuff, and it's confusing to everybody the first time. So don't let that scare you off. But if this is confusing to you, we're going to go over it again in person in the class, and again, we'll have some homework problems on it and stuff like that. And hopefully you get a feel for it. It probably won't ever feel great. It probably won't ever feel great. But I want to leave you with one metaphor that helped me understand this a little bit. This duality principle a little bit. So almost all races I know. No, I'm going to save this for the large group. This is an incentive to show up to the large group class. I'm going to save the metaphor.